All right, the previous question said, for each of the following molecules, we want to count the bonding and the non-bonding electron domains and identify both the electron domain geometry and the molecular geometry. So let's take a look at these. We've got 6 of these to work through, not too difficult. For carbon dioxide, we can see that there are 2 bonding domains around the central atom of carbon. We have no non-bonding domains around the central atom. Therefore, we have 2 total electron domains around the central atom. That makes our electron domain geometry linear, and because it is symmetric, it makes our molecular geometry linear. All right, now we look at BH3. This is a gas commonly called borane. You might call it boron trihydride, but it's commonly known as borane. When we look at that, it's got 3 bonding domains because it's got 3 valence electrons. No non-bonding domains, so a total of 3 again. And because they're all separated equidistant from each other because of Vesper theory, this becomes an electron domain shape of trigonal planar. And again, because there's no asymmetry, the molecular geometry is trigonal planar. Now we go to ozone, O3. This is going to be a molecule that's got 3 oxygen atoms in it. There'll be 2 bonding domains around the central atom, but there will be one non-bonding pair of electrons around the central atom. So a total of 3. And it's also trigonal planar when we look at the electron domain geometry. But because this is asymmetric, we've got 1 single and 1 double bond, this molecular geometry is bent. We look at methane, a pretty simple molecule to look at. There's going to be 4 bonding domains around carbon, no non-bonding pairs, so a total of 4. That makes our domain geometry be tetrahedral. And again, because it's all symmetric, our molecular geometry is also tetrahedral. Ammonia. We have 3 bonding domains where nitrogen bonds to each of the 3 hydrogens, but 1 non-bonding pair. That gives us a total of 4 electron domains. And because it's 4, the electron domain geometry is tetrahedral. But because one of these domains is a pair of non-bonding electrons, the electron repulsion that this pair of electrons exerts on all the other bonding orbitals pushes this down, and this becomes a trigonal pyramidal shape. It's just a 3-sided pyramid. The last one we look at is water. 2 domains bonding around the central oxygen atom, and now we have 2 sets of non-bonding electrons for a total of 4. Because it's 4, the electron domain geometry is tetrahedral, but the molecular geometry again does not take into account the electron domains. It takes into account merely the atoms that are present. The atoms that are present, just 2 hydrogens and an oxygen, that's going to be bent. All right, now we want to fill in the information in the table below. So for the examples on the right side of the table, we're going to select from the following list of molecules and ions. There's quite a little laundry list here. So we're going to try to fill in the blanks. When we have a total number of electron domains around the central atom, when that number is equal to 2, our electron domain geometry is linear. There's really only one case here. There's 2 bonding domains and no non-bonding domains. That makes my molecular geometry linear. And an example of this would be hydrogen cyanide. An example of a polyatomic ion in this category would be the nitride ion, N3-. All right, now we look at when I have 3 electron domains, I've got 2 ways I can break this out. But 3 domains around a central atom, the electron domain geometry would be trigonal planar. But I could either have 3 bonding domains and no non-bonding, or a 2 and 1 setup. When I have the 3 and 0, as we saw on the previous slide, this is a trigonal planar geometry, and an example would be silicon trioxide, and an example of a polyatomic ion fitting this category would be the nitrate ion. But I could also have 2 bonding domains and 1 non-bonding domain. When I do that, that gives me a molecular geometry that's bent. An example of this would be sulfur dioxide, or a polyatomic ion would be the nitrite ion. And then lastly on this slide, we have 4 electron domains, which of course gives us the tetrahedral electron domain geometry. But now I have 3 ways I can do this. Comparing bonding and non-bonding, I can do 4 and 0, 3 and 1, or 2 and 2. And we've seen a lot of this before. When I have 4 and 0, that still stays the tetrahedral shape. An example of this, picking from this list, would be carbon tetrachloride, and an example of a polyatomic ion would be the sulfate ion. When I have 3 bonding domains and 1 non-bonding domain, that's going to be the trigonal pyramidal shape. So my example would be phosphorus trichloride, and my ion that fits this shape would be chlorate. 2 and 2 is going to give me the bent structure, and my example here would be sulfur dichloride with chlorite as my polyatomic ion. All right, now let's go to the next one. We want to explain why the bond angles in ammonia and water are less than 109.5. And the answer is that this non-bonding pair of electrons takes up more space than a bonding pair. And they exert a greater repulsive force because there's just a lot of negative charges, and like charges repel each other. And this tends to push the other bonding pairs down and makes their angle less than 109.5. It's not a lot, just a couple of degrees, but it does change it. Question G, explain why the chlorine-carbon-chlorine bond angle in phosgene, Cl2C double bond O, is less than 120 degrees. All right. Now, in general, electron domains for multiple bonds exert greater repulsive force on adjacent electron domains than the domains from single bonds. Okay, so this is why we're going to end up with this angle less than 120. We would expect a trigonal planar. The fact of the matter is the double bond that oxygen has with carbon pushes the chlorine closer together, okay? And we can see that when we look at this picture here. Instead of 120, it pushes the 2 chlorines down to 111 and opens up the chlorine carbon oxygen bond to be 124. Problem or question H, molecules with 5 or 6 electron domains around the central atom have molecular geometries that are based either on trigonal bipyramidal, which would be 2 trigonal pyramids that are base to base, or octahedral, which would be a 2 four-sided pyramids, which would be base to base. All right, let's label the axial and the equatorial positions on this molecule shown below. I'm not sure what this is. This could be phosphorus pentachloride or pentabromide, but we can see that the axial ones are coming out of the top and the equatorial ones are around the equator, looking at this from the side. Now, because the domains from the non-bonding pairs exert greater repulsion than those from bonding pairs, the non-bonding domains are always going to be in the equatorial positions, okay? It gives them more room to spread out when we do that. All right, next question. We want to fill in the information in the table below. For the examples on the right side of the table, we're going to select from the following list of molecules. This is very similar to what we were doing, only now we've got 5 and 6 domains. So when I look at 5 domains, my electron domain geometry is the trigonal bipyramidal, and I've got several ways this can go. When I look at bonding and non-bonding, I could have 5 and 0, 4 and 1, 3 and 2, and 2 and 3. So let's take these one at a time. 5 and 0 gives me trigonal bipyramidal, and an example, as we just talked about, would be phosphorus pentachloride or SF5 plus polyatomic ion. When I'm looking at 4 bonding domains and 1 non-bonding, this is called the seesaw, and an example of this would be SF4, with the polyatomic ion being PF4 minus. We will look at some models in class to get a better feel for why this shape has the name seesaw and what that really looks like. Now, when I go to 3 and 2, this is called a T shape, and this will be very clear once you see the shape. The example of this will be chlorine trifluoride, and we don't really have any polyatomic ions that have this shape. And then the last one for trigonal bipyramidal is 2 bonding domains, 3 non-bonding domains, and this of course would be linear, and an example would be xenon difluoride or the tribromine anion. Now the last collection of shapes will be when we have 6 domains. That gives us the octahedral shape. And here there are only 3 ways this can go. 6 and 0, 5 and 1, 4 and 2. When we look at the 6 and 0, that's going to retain the octahedral configuration. And a good example of that would be sulfur hexafluoride with phosphorus hexafluoride minus as the polyatomic ion. When I have octahedrals with 5 bonding domains and remove one or add 1 non-bonding domain on the bottom, that gives us a square pyramid shape. It's a 4-sided pyramid. An example of this would be chlorine pentafluoride, and there isn't a polyatomic ion. And then for 4 and 2, that's going to give me square planar. That's going to give me 1 atom in the middle and 4 all bonded around it in a square. This would be xenon tetrafluoride, and an example of a polyatomic ion would be IF4 minus. All right, we're going to stop here. We'll cut this one short and we'll go on to these next questions in the next video.